So what we're going to do is we're going to dive right in. We're going to take a look at three-phase half-wave rectifier, and then we're also going to look at the three-phase full wave. But first, the half wave. So let me go ahead and draw a few things down for you. Now, the advantage of the three-phase rectifiers is that you have a lot more ripples for every cycle, and so what happens is your average voltage is much higher for the same source, same source voltage. So some real advantages to this. And so we're going to go ahead. I'm going to draw the circuit for you, and we'll dig into it. So I'm going to start. We want to look first of all at the facts that have to do with this type of rectifier. First of all, the number of diodes required. Now with this particular rectifier circuit, three-phase, half-wave, we need 3 diodes, just one per phase. And what I'm going to do right away is I'm going to show you what the circuit looks like. Now these are very easy to draw, actually, in some ways even easier than a single phase. So let's start with my 3 lines. Another retired pen. Okay, now we also have in this circuit a neutral, which means that we're going to have a 3-phase 4-wire circuit. Now this is absolutely necessary, 3-phase 4-wire, in order to connect up this half-wave rectifier. So what we do is a very simple matter, actually. One diode connects to the A phase, one diode connects to the B phase, one connects to the C phase, and then you take the other side of these 3 and you tie them all together. Now please avoid thinking of this, do not think of this as a Y connection. Even though we're feeding from a 3-phase, this side, this lower side, is actually DC. So try and stay away from the 3-phase idea on this, even though it does look like something like a Y connection. Now from here, we go, and here is our DC load. And that DC load connects up back to the neutral. So as you can see, very, very simple connection. And here's what happens. As the potential of line A is the highest, current will flow through A. It will then block against this diode and this diode. If this is the higher potential, it will block here and block here. So it has to block literally from A to B and A to C. So it has to block the full line voltage. Now, imagine then this current would come down and it would flow through the load in this way. Now, as the 3-phase circuit moves, A starts going down, B starts becoming the higher potential, and then at that point, the B current would flow. Now it would come down through here. It would block against A and block against C. As the B current starts to fall, then the C current would start to flow here. And you can see then we would have C flowing through the load to neutral. So the entire load current is made up of little segments of A, B, and C current just following each other. But what it does is it gives you a very nice, constant, smooth DC current there. All right, number 3, in terms of our facts is, what do the waveforms look like in this rectifier? And so what I want to show you is, I'm going to start by showing you the three-phase waveform. I'll just try and freehand this. Give myself a little reference line here. Okay, this is the load, which we call the output, and this is the source, which we'll call the input. And what we have is A starting here, B starting 120 degrees later, and C starting 120 degrees after that one. Now this is going to look very familiar to you now that you've already done three-phase theory. Now what happens is, the positive alternations are the only thing that is seen by the load. These negative alternations are blocked by the diodes. And so what we're going to actually see for a waveform over here is going to look like this. Okay. And so what we're going to see, our output is literally going to be 3 ripples per cycle. Okay, 3 ripples for every cycle of three-phase power. Now, there's something that's very important to note, and so I want to show you this. When we look at this three-phase waveform, the voltage that we are seeing here, this three-phase AC that's being applied to the actual load, is the phase voltage. Okay, so you really need to be aware of this. Why is this three-phase the phase voltage? And the reason is that the diodes all go from line to neutral. Remember what it looked like: A, B, C, diode 1, diode 2, diode 3, joined together. Then we had the load and neutral. So if you look carefully at that diagram, what you're going to see is that the circuit is very definitely from line to neutral. So just let me give you this example. If this was 208 volts, three-phase, then we could look at this and we could say, well, what would the peak of the 208 volts be? And so, because we always like to know what is the actual peak of the waveform. So if I go 208 times root 2, I'm going to see about 294 volts. So this would have an E peak of 294 volts. But in fact, the voltage, these waveforms that we're looking at right here, are actually the voltage from line to neutral. And so the voltage from line to neutral, as you can well imagine, if this is 208, this would be 120. So how tall would this peak actually be? And so many of you are going to be ahead of me on this one. But in fact, the peak of these waveforms right here is going to be 170 volts. Now this is very important when it comes to figuring out what our average voltage is, and what our peak-to-peak voltage is, and so on. Okay, so remember, specifically with the three-phase half-wave rectifier, the voltage that is applied across the load is going to be the phase voltage. And so the peak of that waveform is going to be the peak of the phase voltage, not the line voltage. Now, when it comes to the PIV of the diodes, those are going to be based on the peak of the line voltage because they're not blocking to neutral. They're blocking line to line, line to line. Okay, so the PIV is going to be based on the line voltage, whereas the average voltage waveforms are going to be based on the line to neutral voltage. Okay, what we need to do now is we need to take a look at how we determine the form factors. And I'm just going to do a quick little review. I brought out the lobster cookers again. First of all, here is the single phase half wave. And in that arrangement, we have our lobster cooker and we only have one alternation of ice formed in there. In a full wave, we have both alternations in there. And now when we get to the three phase, guess what? We now have three ripples. So essentially three of our waveforms, and they're overlapping. Now the interesting thing is that in the single phase half wave, it goes from 100% to 0. In the single phase full wave, we still get to 0 down here. So 0 is still our lowest point. Now in these ones, something interesting happens. The lowest point is actually right there because of the overlap. And so now we're going to wind up with a lot more in this one. Once we melt these down, we're going to see a lot more volume here. And I'm going to talk about specifically what the numbers are. But let me first of all just show you the form factors. And this is a little bit of a summary, okay? In this one, it's E line times 0.45. Then we move to the single phase full wave, twice as much. So it's E line times 0.9. And we talked about this in the last session. Now the form factor for the three phase half wave is E line times 0.675. And I'm going to show you in a little bit of detail how we arrive at that number, but these are the form factors that you really need to be able to remember. And remember, form factors are always a relationship between the average voltage and the line voltage. So even though the half wave rectifier is from line to neutral, this value, this form factor is actually based on the line voltage. So when we go to calculating that, we'll you know, that'll make a little bit more sense. Okay, now that we've got, I've put up a little example circuit here, and we're going to work through it, and we're looking at item number 4 here, which is essentially the specs that would go with this, the specs and calculations that would go with this half wave rectifier. So let's go through them one by one. First of all, the form factor we just talked about. The form factor times the line voltage will give you the E average. And so in this case, if we look at the E line, which is 480 volts, and then we multiply that by 0.675, we should get about 324 volts here, DC. Well, that's quite a bit of voltage comparing, well, you know, we're always looking at some fairly low numbers with the single phase. Now, granted, one of the things that happens is in three-phase circuits, we quite often have the three-phase voltages are quite often higher voltages. But even regardless of that, we're definitely getting a much higher percentage of voltage for the load. So 324 volts would be the DC load voltage. Now, 324. Now, how much current will that develop for us? And so what we look at is we take the 324, we divide by 12, and we come up with a current of 27 amps DC. 27 amps. Now, when it comes to the current per diode, we need to realize just one thing. This current looks like this. 27 amps from the A phase, then 27 amps from the B phase, and then 27 amps from the C phase. And then, we chase that again with the A phase current again. But what it really means is that this diode is only conducting for, roughly speaking, maximum 120 degrees of the cycle. Then 120 degrees here, and then 120 degrees here. And so, it's rising and falling during that time. So when we look at it, we go, well, really, these diodes are only working about 1/3 of the time. And so, in fact, the current per diode is I load divided by 3. So in this case, that's just 9 amps per diode. So your diode rating would only have to be 9 amps to support that load. Now the frequency of the ripple, of course, is based on this. What does our waveform look like? Well, it looks like this. There's our 3 ripples per cycle. And so if we start here with a 60 hertz, which we would typically be looking at there, we would have now a ripple frequency of 180 hertz, or 3 times the source frequency. Now, a little earlier, I believe I mentioned that the PIV, the peak inverse voltage rating of these diodes, is the only thing here that, they really are blocking line to line. So in other words, when this one's conducting, it comes into this node right here and has to block the full line to line voltage against these two. Not both at the same time, of course, but at some point, each one of these diodes will experience a full line to line voltage. And so what we need to do for the PIV is we need to use PIV is going to be E line times root 2. We have to be as large as the peak of the line voltage. Now at 480, that's going to give us quite a lot of voltage, 679 volts. 679 volts will be our PIV. Now, what about let's talk about the power of the load. And the reason I like to pick that one off right away is that in 3-phase circuits, the load power is very, very nice to calculate, much easier than the single phase problems. And what we're looking at for power, now this is for both the half wave and the full wave, so you can mark this one down. Power total is equal to the voltage of the load, so in other words, the DC voltage times the current of the load. So the DC load current and the DC load voltage, and that's it. So in this case, we would be looking at E line, the E of the load is going to be 324 volts. So 324 times 27, and this of course is going to equal quite a bit of power, 8,748 watts. All right, so lots of power there. But the main thing to realize is that in 3-phase circuits, this power is very, very simple to calculate. So we don't have to worry about using line values, so we don't have to worry about making any divisions, even though it's a half-wave rectifier. So we're just looking at voltage times current. All right, there's only 2 points left here that we need to talk about. One is the peak to peak, otherwise known as the ripple voltage. And we need to talk about what is the minimum voltage. Now in the single wave and the single phase, half wave and full wave rectifiers, we always had a minimum voltage of 0. Now, that's not the case in the 3-phase rectifiers. And let me just show it to you like this. Now I've drawn in the A, B, and C ripples, and in the example that we were looking at, we had an E line of 480 volts, 480 volts. And that means that E phase, somebody with a calculator can work that out, or you may actually have this one memorized. E phase is 277 volts, okay, 277 volts. Now, if E phase is 277 volts, then what I would like to know is what is this voltage indicated by my red line. Okay, so we'll be going, okay, we have 277 volts is the phase voltage times root 2, and that will give us the peak of that. And interestingly enough, that works out to 391.7 volts. So 391.7 volts. And so we go, okay, so what is the minimum voltage? Well, if this is 391, this is 0 volts down here, but I want to show you something. The voltage never drops lower than this point, and the reason is that the voltage from A, as it's falling, when it gets to this point, the voltage from B is actually rising, picks it back up again to the peak, comes down. When it gets down here, the voltage from C starts rising. So the voltage never actually falls any lower than this line right here. And what we want to now, what we need to do is we need to figure out, well, is there a predictable way to know what that level of voltage is? And I've tried to make it a little bit, to scale so you can kind of guess. But what we really want to do is we want to calculate it. So let me go ahead and show you how we're going to do that. You know what I'm going to do? I'm actually going to show you an example using a peak of 100 volts. I'm going to do it right here, just as a little mini lesson. If I have a peak here, one waveform, and I have another one here that starts 120 degrees later and goes up and then comes back down again. First thing that we need to look at is from the point where this one hits its peak to the point where this one hits its peak, this distance is 120 degrees of time because of the three-phase system. Now what that means is that from this peak to this lowest point, in terms of time, this time right here is just 60 degrees. So it means that the voltage is at its peak of this waveform, and then it falls for 60 degrees, and that's when the rising voltage of the next ripple is coming up. Now, how much does voltage fall in 60 degrees? And so what I would say is, if you look at it like this, I'm going to make it a nice easy number. Let's say that this peak was 100 volts. 100 volts. When it has gone from peak, it's gone for 60 degrees, how far down, what is the actual value, the instantaneous value at 60 degrees? And so if you go cos 60 degrees, you're going to find that this value is actually 0.5. Okay, 0.5. And so that means that the voltage right here in this little mini example that I gave you, this voltage would be 50 volts. That would actually be the minimum voltage. Now, with that being said, let's look at this example. If we have 391.7 volts, that means that the minimum voltage, or the lowest that we'll ever see this voltage drop to before the next ripple comes along and pulls it up again, is 195.9 volts. 195.9 volts, and that's actually the minimum voltage. Okay, that is the minimum voltage in the circuit. Now, what is the peak-to-peak voltage? We know that the peak-to-peak voltage is actually the most positive point to the most negative point. And so as you can see, really, if you take a look, the 391.7 is the highest voltage or the most positive point. 195.9 volts is the most negative point or the lowest voltage. And so the difference between these two is actually the ripple voltage. Now, seeing as this lowest point is 50%, what we know is that, from 0 to 195.9, and this is our minimum voltage. And so we actually have a peak-to-peak voltage of the same value, but it's the top half. So the ripple voltage or the peak-to-peak voltage is also going to be 195.9 volts. It's going to be the top half. And if we were to look at this on the scope, what I want you to see is this. What we would actually see, and we're going to see this in the lab when we do this, you won't see any of these lines. All you'll see is a zero reference line. And you will see then a row of ripples on your scope that look just like this. And so we call this ripple voltage. This is the ripple voltage. This is the value that this is what you'll actually see. And we go, and so this portion here, completely full of voltage. And this up here, you still have some little valleys in there, but it does give you a nice high level of average voltage. In this case, 324 volts, which is obviously up into this range up here somewhere. Okay, so the average voltage actually somewhere here at about 324. Okay, and that's the load voltage. So, that kind of wraps that up. Those are the main key sort of stats points, and we see where they come from, where those numbers come from. And so what we're going to do is we're going to go ahead and move on next into the, we're going to take a look at the full wave, which we call a 6-pulse. This rectifier right behind me is called a 3-pulse. So the half wave is called a 3-pulse because of the 3 ripples. Now we're going to move on to the 6-pulse. Okay, now what you're looking at is this is a 6-pulse, 3-phase full wave rectifier. We're going to use 6 diodes, and I've shown you the connection. So what you have is you have a 3-phase line. There's no neutral required for this one, just line voltage. All of the diodes are connected line to line. And so you'll see that if you follow from A would come down into the anode of a diode, B would come down into an anode, and C would come down into an anode right here. Now these three connect, the cathodes connect together, feed one end of the load. From the other end of the load, we go into anodes, through the diodes, and the cathodes connect back to A, B, and C on the line. And so that's the connection, actually very simple. If we look at the voltage that has to block by these diodes, it's still line voltage A. If we're flowing through here, we have to block here and here, and so our PIV will be based on line voltage blocking. But our actual waveform of voltage across the load will also be based on line voltage, because at any point in time we know that this the way that the potential will work is that this will be from A to B. Then the next, in the 120 degrees later, it will be from B to C. And then 120 degrees later, we'll start at C. It'll come through and to A. And so that's, we'll get our A to B, B to C, C to A, which is our line-to-line paths through the rectifier. And so that's what we'll be doing. Now we're going to go ahead and start. I'm going to show you the waveforms in just a moment. Okay, what I'm going to do now is I'm going to show you the 3-phase waveform. I'm going to start with the AC, the AC would look like. And then I'm just going to modify it to show you what the DC. So let's just go ahead and I'm going to try and draw a nice even three-phase waveform on here. Okay, 120 degrees later, I'm going to come along here with B. It's going to come up. It's going to come down here. It's going to go negative, cross A right there, come up here, cross A up here, now going positive. I'm going to continue this backward this way as well. This is going to come down here negative, like that. Now, let's go ahead with our C phase. C phase is going to come in here. It's going to rise right here, come up to a peak, cross A phase here, back down, going negative, crossing the B phase right there, coming back through 0. Now, in this side, coming down, crossing the A phase, negative peak right there, crossing the B phase, going through 0, crossing the A phase here. And I think we have enough there that we can find a cycle. And so, as you're aware of, a cycle is simply the point in a waveform where where a waveform starts to repeat itself. And so what I'm going to do is I'm going to look, I want to make sure I get a full cycle here to count. And I think what I'm going to do is I'm going to start right here. That's going to be the beginning of my cycle, right where the C and the A cross each other. And that means that the exact end of this waveform is going to be right here. That is one cycle, exactly. Now what we'll see is that seeing as this is a rectifier, this is what the AC input would look like. So we have, I'm going to write these down here. We have positive A, we have positive B, and we have positive C. And what we'll also have is this one down here, which I'm just going to take it out. This A, I'm going to dot that out. That A actually gets flipped, and so it will sit right up here, in fact, like this. So that's the inverse of A. I'll call that negative A. Now, this negative C right here will also flip over. This is what the diodes do. They flip this waveform over. So that means I'm going to have a C that's going to come up right here. It's going to cross there like that, and it's going to come back down here. Okay, I'm going to call that negative C. Now, B, we have right here. And I'm going to also flip it over, and it really sits just like this. And we're actually, because of the way the cycle is sitting, we're going to have half of that B alternation here. And because we need to have a complete ripple, it's actually going to go right here. So you can see that we have here actually 1, 2, 3, 4, 5, and half a ripple here and half a ripple here, giving us a total of exactly 6 ripples in that one cycle. 6 ripples. Okay, and so what we've done is we've really flipped over all of the negative alternations, and now we have a nice, a nice row of 6 ripples, and the minimum voltage is at a very, very high level. Now what I'm going to do is I'm going to clear this off, and I'm going to do a little bit of a better example of just looking only at the top, and we're going to compare some numbers. Okay, what I've done is I've just redrawn this. We just want to look at the ripples, and we want to establish some values here. Now, we want to look at what the form factor is. And so just in this particular case, I'm going to give you the line voltage just so we can write some numbers in. And so I'm going to say, what would happen if I had an E line of 600 volts? Now that's a fairly common three-phase voltage, 600 volts, three-phase. What would E peak be if I had 600 volts? And so many of you are going to grab your calculator and you're going to check this out. So 600 times root 2, and you're going to have 800, and I'm just going to round this to 849 volts. 849 volts. Now, what the next thing that we don't want to determine is, well, what is the minimum voltage actually? Now the minimum voltage is represented by these little lines right here. You can see as one waveform is falling, boy, it doesn't come down very far, and the next one picks it up again. Really, really, just a small amount actually of change from the peak to the minimum. And this is an interesting thing actually about ripple voltage. The higher the number of ripples are, the actual lower the magnitude of the ripple voltage. So the ripple voltage gets smaller and smaller. And I'm just going to show you in blue, just on a little part of it here, what the ripple voltage would actually look like. This is what the ripple voltage actually looks like. If you were looking at this on your scope, all you would see, all of this would be blank, and you would just see like a little ripple up there and then your zero reference line. So this is actually the ripple voltage right up here. So how do we figure out how much that ripple voltage is? That's one of our tasks. So let's look at it this way. From one peak to the next peak, now that we have 6, that's going to be 60 degrees. And so what that means is that from any peak, from this point here, from the peak to the lowest point of that valley right there, is only 15 degrees. So you can go ahead and you can grab your calculator, cosine of 15 degrees. So if you start at 849 volts and that voltage only falls for 15 degrees, what is the level of voltage that you will have right here? And that will be our minimum voltage. Now, hopefully what you discovered is that that is going to be 86.6% of 849 volts, which equals 735 volts. Okay, so 735.2 is E minimum. And what is the difference? Well, you can simply take 849 minus 735, and you're looking at about 113.8 volts. 113.8 volts, and that's your peak to peak or your ripple voltage. What is the minimum voltage? 735.2 volts. The voltage in this waveform never drops lower than 735 volts. This is why we're going to have an exceptionally high value of actual average voltage, because where is the average voltage going to be? I'll show you, just making a line right in here. The average voltage is actually going to be right up here, right along this line. Now, the form factor that we're going to use for the full wave 6-pulse rectifier is going to be E line times, and you remember that with the half-wave rectifier, it was E line times 0.675. Well, Now we have 6 ripples instead of 3 ripples. So yes, you're right. It's going to be 1.35. It's going to be the line voltage times 1.35. So let's just make a quick note of that form factor, 1.35. And that is the form factor for the 3-phase 6-pulse rectifier. In this case, giving us an average voltage of, well, what was the line voltage? We were looking at 600, right? So 600 times 1.35, and it is 810 volts. 810 is our actual average DC voltage from a 600 volt 3-phase system. So that's a lot of DC voltage, and this is why the 3-phase circuits, you know, from admittedly the 3-phase voltages are typically higher, but that's a lot of load voltage, and so we're going to get very smooth. A very smooth ripple, so it's a nice smooth voltage. It doesn't take very much filtering because you only have these tiny little valleys to fill in, and you're going to have nice high voltage outputs, and it's going to give you a nice high amount of power. And remember, with the 3-phase full wave, this is also going to be the power, same as in the half wave. It's just going to be E of the load times I of the load gives you the power, and just very straightforward. Okay, I've actually filled back in the drawing, and we're going to finish off item number 4, which is just kind of the specs and the calculations that have to do with this circuit. So you can see I've replaced again the 3-phase 6-pulse rectifier. We have our line voltage of 600 volts, which corresponds to the values that we had over there. 1.35 for our form factor. We've already calculated that we have 810 volts as a 810 volts as a DC load voltage, and the resistance that we have here is actually 16.5 ohms. And so we'll go ahead and we'll figure out current, and we'll figure out power based on that, 16.5 ohms. So let me just quickly check then. What we need to realize, the current, of course, is just going to be the DC current based on the voltage and the resistance. So 810 divided by the 16.5 ohms, giving us a current of 49 amps. 49 amps. Now remember, that current is flowing in little segments. Each segment is 49 amps, but it's timing. It's 1/3 of the time here, 1/3 of the time here, 1/3 of the time here. And so in fact, if we take the 49 and divide by 3, we're really looking at about 16.4 amps per diode. 16.4 amps for the rating. Now, does that mean that it's actually 16.4 amps going through the diode? Absolutely not. The current going through the diode is 49 amps, but it's only going through it for 1/3 of the cycle. And so we can derate it to, because we've got 1/3 of the time heating, 2/3 of the time cooling. So we can actually rate it quite a bit lower. Okay, so current rating of the diode, 16.4 amps. Frequency of the ripple. We looked at it. 6 ripples is going to give us a ripple frequency of 360 hertz, or 6 times the supply frequency. The peak inverse rating, the peak inverse voltage rating of each one of these diodes. Well, at any point in time, 2 of the diodes have to block against the other ones. And so in fact, what really happens is, I'll just show you current-wise what happens. When A is flowing here, that same current is going through this diode here. So as it comes through here, it's actually blocking against this diode that goes to line B and this diode that goes to line C. And over here, it's actually flowing to B on the other side of the resistance. And And so really the point where the main line-to-line voltage blocking is going to be is here. Then when we go to the B current, it will come through here and back to C. And then when we take and look at the C current coming this way, here's the C current, and it flows through and goes back to A. Okay, as they happen in their 120-degree cycles. So the PIV is going to be the peak voltage, so 600 times root 2. 600 times root 2 will be the PIV rating. PIV equals 600 times root 2. And let me just run that through. And we're looking at 849 volts. 849 volts. Something tells me we had previously looked at that as well when we were looking at the waveforms. 849 volts. Now, the power of the load, very, very straightforward calculation. We're simply looking at the voltage and the current of the load. It's going to be a lot of power, 810 volts times 49 amps. And it's 39.7 kilowatts. So as you can see, in a lot of ways, the three-phase full wave rectifier may be actually one of the easier ones to draw. Definitely very straightforward in terms of calculating the power. And the main thing that we're going to need now is we're going to need just a lot of practice. And there are going to be quite a number of these three-phase half wave, three-phase full wave, single phase half, and full wave rectifier problems for you to practice on. And I understand we're going to have some time also where we're going to, you'll be able to ask me some questions. We'll be able to talk about them a little bit. So there you go. That's the three-phase full wave and half wave rectifier.